We have learned two methods for the systematic analysis for the complex circuits previously, that is branch current analysis and node voltage analysis. For the branch current analysis, we need B equations, which are B minus n plus 1 KVL equations and n minus 1 KCL equations. Compared with the 2B method, the equations number of this method has already decreased by half. While for the node voltage analysis, we only need n-1 KCL equations because in the node voltage analysis, KVL equations are satisfied automatically. The number of the equations is correspondingly reduced. Then we will think naturally that whether there is a method that only needs Bn minus n plus 1 KVL equations and we no longer need the KCL equations. In fact, this method is called the loop current analysis we will learn next. We will find that in the loop current analysis, the number of the equations is B minus n plus 1. It is actually equal to the number of the independent loops in the circuit. The so-called loop current analysis is a method writing equations in terms of the loop currents. For example, in this circuit, there are two independent loops. We can choose the two meshes as a set of the independent loops. Here, one point needs to be emphasized. That is, the loop current doesn't exist in the real circuit. It is a variable what we assumed just for the circuit analysis. It is different from the node voltage. The node voltage actually exists in the circuit, and we can measure it by the voltmeter. While there is no such a variable, the loop current in the circuit, what we can measure are the branch voltages, the node voltages, and the branch currents only. But with such a hypothetical variable, we can express the branch currents in the circuit by the linear combination of these loop currents. Okay, after selected loops, we assume that the two loop currents are IL1 and IL2 respectively. Then we can write the KVL equations along the loops with certain directions. For simplicity, along loop directions, we use the voltage drops. We write KVL equations for these two loops. That is, the sum of the voltage is 0. Of course, it also can be written in another form, that is, on the left side of the equation, there are the voltage drops across all the resistances, while on the right side of the equation, there are the voltage rise across all the voltage sources. With this B minus n plus 1 equations, we can find the B minus n plus 1 loop currents. The key is that with these loop currents, we can express the real branch currents in the circuit by the linear combination of them. For example, in the circuit, after determining the two loop currents IL1 and IL2, we can see there is only one loop current IL1 flowing through branch 1. So branch current I1 is equal to IL1. But for branch 2, both loop currents flow through it. According to the present reference directions, it should be I2 equals IL2 minus IL1. Similarly, there is only one loop current flowing through branch 3, so I3 equals IL2. Please think about it. Why KCL equations are no longer needed in the loop current analysis? I just remind you, it can be proved according to the principle of current continuity. As the name implies, the loop current is the current flowing in the loop. When it flows into a node, it must flow out of the node from the other branch. So KCL equation is satisfied automatically. Well, here we take this circuit as an example. we will explain specific steps for the loop current analysis. First of all, we select the two loop currents. Then we can write the KVL equations along the loops with certain directions. For loop 1, it should be R1 times IL1. The voltage drop across R2 should be R2 times IL1 minus IL2. And on the right side is the voltage rise across all the voltage sources, which should be US1 minus US2. For loop 2, we can similarly write its equation. Along the loop direction, the voltage drop across resistance R2 is R2 times IL2 minus IL1. And the voltage drop across resistance R3 should be R3 times IL2. On the right side, along the loop directions, the voltage rise across all the sources is US2. Note that we write the equations always in terms of the loop currents. These three branch currents shall never appear in the loop current equations. Okay, we rearrange these equations by incorporating the coefficients of IL1 and IL2, then we get such a form. It is actually the standard form of the loop current equation. We can write them like this. This coefficient is R11 and this coefficient is R22. This is R12 and this is R21 accordingly. Now let's take a look at it. What's the physical meaning of each coefficient? For R11 and R22, R11 equals R1 plus R2. That is the sum of all the resistances in loop 1. R22 equals R2 plus R3 is the sum of all the resistances in loop 2. We call it the self-resistance of loop 1 and loop 2, which is the sum of all the resistances in the loop. R12 is minus R21. It's minus R2. R2 is both in loop 1 and loop 2, or in other words, both loop currents IL1 and IL2 flow through this branch, and the directions of the two currents flowing through R2 are opposite. So we call R2 the mutual resistance of loop 1 and loop 2. Because the directions of the two loop currents flowing through the mutual resistance are opposite, so add a minus sign in front of the mutual resistance. The right part is the voltage rise across all the voltage sources along the loop directions. This conclusion can be extended to the circuits consisting of L independent loops. We write it as a standard form, wherein the diagonal elements RKK, that is R11, R22 until RLL, we call them the self-resistance of loop K. It is always a positive value, which is the sum of all the resistances in loop K. While the non-diagonal element RJK is called the mutual resistance of loop J and loop K. Different from the mutual conductance in the node voltage analysis, which is always a negative value, there are several possible values of the mutual resistance. For the loop currents flowing through the mutual resistance are with the same direction, the mutual resistance is positive. And if the loop currents flowing through the mutual resistance are with opposite directions, the mutual resistance is negative. Of course, if two loops have no common resistance, their mutual resistance should be 0. Similar to the node voltage analysis, when the current does not contain the dependent sources, the coefficient matrix of the standard form of the loop current equations also should be symmetrical. That is, RJK equals RKJ. The right part is the voltage rise across all the voltage sources along loop K of the same direction. After we have understood the physical meanings of each coefficient, we need not write the equations from the very beginning of the KVL. We can directly write the standard form of the loop current equations. This is very useful when writing large number of equations for solving complicated circuits. For a planar circuit, similar to the loop current analysis, there is a method called the mesh current analysis. We know that the meshes of the planar circuit can be chosen as a set of the independent loops. Then the loop current correspondingly become the mesh currents, and the analysis method is called the mesh current analysis.